As you can see, because of last time, we literally have a clean slate in front of us. So let's back up a bit, take it back to the start and talk about the how and the why of rocketry. Whenever you do engineering projects, you always want to have your why in the back of your mind. I'm talking about what the specific motivation of what you're trying to do is. It's pretty hard to drive a car without knowing where you're going, and the same is true when you're trying to drive an engineering design. So then I guess you're asking yourself, why build rockets? Because they're awesome. Now don't get me wrong, that is a good enough reason, but it's not really going to help us in our design. Really, what we want to be doing is launching payloads into the sky. Based on the comments from the last video, it seems like a few of you want to see warheads. Now, to be perfectly honest, I think it's best for me to stay out of prison, so we just aren't doing that. We will eventually start working towards some cool payloads, but first we need to develop all the systems in the rocket that surround the payload in order to take it up. So if we're just moving an object from the ground into the sky, it really just becomes one of basic mechanics, which is the study of motion. So how do objects move? We experience a three-dimensional world, so all objects can move in 6 different ways. We call these degrees of freedom. They can move linearly in the 3 X, Y, and Z axes, and they can also rotate about these 3 axes. They're called roll, pitch, and yaw respectively. Let's recall our mission, get stuff into the sky. That means we care most about this X-axis. Now, what equation governs this motion? This guy is back again. And there's a reason for this. This equation pretty much underlies everything about mechanics. And essentially, it's the only maths we really need to know. So this means that the acceleration of the rocket is equal to the force applied to it divided by its mass. Very broadly speaking, the more we accelerate an object, the higher it's gonna go. So realistically, to maximize the performance and lift as much stuff as high as possible, we need to maximize this number. This equation is sometimes misinterpreted. Really, it should be sigma F, which means the sum of all the forces acting on it. So then we can break this sum up into the forces that propel the rocket forward and those that are holding it back. So to get the highest performance we can out of this rocket, not only do we need to maximize the force that's being applied from the propulsion system, but equally as important, we need to reduce the amount of force that's holding it back. For our purposes here today, we can break up the forces holding the rocket back into 3 distinct sources. The first of these is its weight. Obviously, the more massive it is, the more gravity is going to hold it down. The next 2 forces are due to the drag of the rocket. These 2 components are the pressure drag, which has to do with the cross-sectional area of the rocket, and the viscous drag, which has to do with the surface roughness of the body. Essentially, the fatter you make the rocket, the more air it's going to have to push out of the way, and the rougher the surface, the more the air is going to want to stick to it as it goes past. Now we're going to do a little demonstration on just how important drag is. But first, all right, now we're ready. So essentially what we're going to do is run 3 different scenarios with this slip and slide. In each one, I'm going to have the same mass and also push off the ground with the same force. The difference will be on how much drag we create. So the first scenario we're going to do is just full spread eagle. What am I doing? You just slow down right away and you don't get very far. So instead, let's get a more streamlined position and just reduce the amount of frontal area we have going into this. It's a little bit better, but we're still not making it off the mat. We also need to reduce the amount of friction this beautiful chest has against the plastic here. So to do that, did you just see that? I got fucking sent and we pretty much had to do no extra work. The reason I think that drag is so often overlooked is because it's not sexy like thrust output or mass reduction. Like, I mean, how can you not find this sexy? But at the end of the day, it's like so important because it's just free energy that you're throwing away for nothing. Now's probably a good time to say, if you want to learn about rockets, but you still want to get in, your daily intake of softcore porn, you know what you have to do. Like this video, subscribe to the channel. What the hell? Even share it with a friend. It helps more than you know, and it allows me to keep making these videos for you guys. All right, that's enough of a tangent. Essentially, this is going to dictate what we need to be looking towards when we're doing our design. All of this is to say we need to make it strong but light, and then smooth and slippery. Okay, let's get back to that discussion about degrees of freedom we started a while back. So we briefly touched on the maths about how we make this rocket go up. But in reality, we're really talking about how to make the rocket go forwards. It doesn't necessarily have to go upwards, as we've seen before. We also want to control how the rocket's going to be rotating during its flight. Specifically, we need to stop it from either pitching or yawing, because it's these two rotational axes which will actually throw the rocket off in its flight. Now, just like before, there is a rotational equivalent of Newton's second law, which says that the sum of the torques is equal to the moment of inertia times the angular acceleration, but that's already too much maths for us at this level. We don't really care about that. If we were actively controlling this rocket and we wanted to choose how much the rocket rotates at any specific time, yes, we would need to know said values. And don't worry, we will come back to that in the future. But for now, we just want the rocket to have a straight flight, aka have zero rotation. So I guess that begs the question, is there any way in which we can design this rocket such that it flies in the straight line without having to do any of the maths? I'm glad I asked, because there is. It's called passive stability. To understand this, we're going to need to introduce two new concepts. First, most of you will be familiar with an object's center of gravity. This is the average location of the weight of an object. Let's say we divided this rocket up into tiny little bits and pieces. Each one of these pieces would contribute a weight at a certain location. And then once you accounted for all of these, there'd be an average somewhere in the middle. The important thing to know about the center of gravity is no matter how large the force or where you apply it, the object will always rotate around this point. The next thing we need to know about is the center of pressure. And in many ways, it's analogous to the center of gravity. Essentially, it's the average location of pressure acting on an object when it moves through a fluid. So just like before, we can divide the surface area of the rocket up into tiny little segments. And as the rocket moves through the air, it applies a different pressure to each one of these segments. The important thing to know about center of pressure is once we average out all these forces, the resultant force is applied through this point. It's the relationship between these 2 points that's actually going to determine whether the rocket's stable or not. Let me show you how. Okay, for argument's sake, the center of gravity is going to be somewhere near the center. Let's just say there. And as we said, the rocket always rotates around this point. Now, let's imagine the case where the center of pressure is actually above the center of gravity. And let's imagine there was a gust of wind to the right that just pushed it off a little bit. As you can see, now the left side of the rocket is more exposed to the airflow coming down. So there's going to be a resultant force that's to the right. If we then go ahead and apply this force to the rocket, it's actually going to continue steering off course, which means more surface area is exposed, therefore creating a greater force to the right, and we're going to spin out of control. We say that this rocket is unstable. Let's imagine now that we design the rocket so that the center of pressure is actually lower than the center of gravity. Let's run that same scenario. A gust of wind comes in and pushes the rocket to the right. Just like before, the left side is exposed. So we're still going to get a force that's pointing towards the right, but this time it's actually lower than the center of gravity. So if we just apply this force, it's going to correct the rocket back to pointing straight. Let's say it overcorrects accidentally and this force pushes it too far to the right. Now the right side is exposed and we're going to get a force to the left, and that's going to keep it straight. So long as our center of pressure is always behind the center of gravity, as the rocket gets knocked off course on its way up, it's always going to correct itself back to shooting forwards. One thing we should note here is that both of these points aren't fixed. As the propellant gets shot out, you can imagine that the center of gravity is actually going to shift forwards because we're losing all the mass of propellant down the bottom. As the rocket actually tilts, because the center of pressure is dependent on how the rocket's actually hitting the airflow, this point is also going to move around. So we want to design the center of pressure far enough back to where, as it moves around, it never crosses this point in any of its flight, or else we'll have something like this. We'll come back to how we actually work out where these points are in the next video. So we now know how to get the rocket up and also how to keep it going straight. Let's talk about those other 3 degrees of freedom, starting with the YZ axis. To analyze these 2 axes, we're going to use a little magic called idealization. It's one of the important tools engineers use to actually be able to solve anything. There are millions of different states this rocket can be in, but what we're going to do is we're going to use assumptions, so we only have to analyze the exact case we want. First assumption we're going to make, the rocket is flying dead straight. And it's fair to assume this because we said we're using passive stability. On top of this, we're going to assume that the rocket's perfectly symmetric. The combination of symmetry and the airflow hitting the rocket directly means that whatever's happening on this side is going to happen on that side too. And we can just cancel everything out. The only other potential source of side forces we have to care about is the wind. But the force of the wind is so small in comparison to that coming from the motor that we can just simply ignore it. And through idealization, we don't have to care about what actually is happening The final degree of freedom is that roll axis. If we look at the rocket from above, no matter how much we spin the rocket, it's not going to get thrown off its course. It's just going to look like it's turning on the spot. So as it's not affecting the straightness of the flight, we're just going to ignore controlling it for now. There are cases in which you would want to prevent the rocket from rolling, and we'll come to that in the future. All right, that was a quick little debrief in how rockets move. Let's now move out of the theory into practice and discuss how the are we actually going to build these things. As we've said before, at a baseline, amateur rockets can be broken up into three major systems. These are the propulsion, structure, and recovery. Essentially, all the propulsion system seeks to do is to apply that forward force on the rocket. In practice, we can literally do whatever we want to achieve this. Like, even if you could blow hard enough on your rocket to get it up, that would count as propulsion. Wait a second, scratch that, that sounded wrong. When you and I talk about rocket motors, we're generally referring to chemical propulsion. This means we use high energy reactions to produce super hot gas at super high temperatures and then just shoot all that out the arse end of the motor. Newton's third law says we get pushed the other way. You always want to design around the rocket motor, and this is because it's generally the most inflexible constraint in your design. What I mean by this is once you pick the size as well as the thrust output of the motor, everything else about the rocket kind of depends on these values. So just keep that in mind. Cool. Let's now talk structure by rummaging through the remains of the theory. As we said before, we want the structure to be strong but light. Therefore, this whole rocket is made out of composite materials. So from the nose down to the back is fiberglass, and then these fins are carbon fiber. Starting with the nose cone at the front, all we want to do is just redirect the flow around the body of the rocket. To do so, we just create a shape that's pointy at the top and same diameter of the rocket below. Now, there's a lot of different profiles you can pick to how you actually create this shape, but to be honest, the difference is just non-existent. Like, if this guy has the dictator designing his rockets.
It is too round on the top. It needs to be point. Round is not scary. Pointy is scary.
Supreme Leader, the shape of the missile top has nothing to do with aerodynamics. It is about the payload delivery.
Everyone thought it would be funny if we made the rocket more pointy, so we did.
Is it better to be pointier? Like, if it wasn't for the
It's
movement.
arguably slightly worse. But like,
I will say though, there was this German guy who mathematically proved that the von Karman is the coolest looking profile, and hence it does go the fastest. Next, we have the main tubes of the rocket. So this is comprised of external tubes on the outside and your internal coupling tubes. We want to manufacture these pieces so that the internal tubes slide nice and snugly. Moving on to the end, we have fins. Now on the surface, fins seem pretty dumb because you're just adding extra mass and extra drag for your rocket to deal with. But they have a pretty critical purpose. Remember how we were talking about center of pressure before and how we said it was an average of the distribution of the surface area? Well, that's what these do. We're pretty much adding a whole bunch of surface area at the back of the rocket so that the air preferentially pushes down here, which means that we can get that corrective force. They may seem pretty sophisticated as they're flying, but at the end of the day, rockets are pretty much just a bunch of tubes and plates. Finally, we have the recovery system, which is a combination of electrical and mechanical components to get the rocket down safely. Let's start by talking about the electronics. Their role is to detect how the rocket's moving and then release the parachutes at the correct time. How do they do this? With a little thing called air pressure. As we know, the higher you get up in the atmosphere, the lower the density and the pressure of the air is. This is because Earth's gravity is trying to pull all these air molecules towards its surface. So there's a decreasing gradient of air the further away you get from Earth. And once the computer's detected that the rocket's taken off, it will start to periodically read the air pressure. As the rocket flies up, the pressure will begin to decrease until it gets to its apogee, where air pressure will come to its minimum. Once the rocket starts falling back to the Earth, the pressure will start to increase, and that's when it'll know to deploy its parachute. So how do we get the parachutes out? Explosions, of course. In here, we have a whole bunch of black powder, and I'll give you a little demonstration on how it works. If we just simply set this on fire, it's going to create a lot of heat, but can't really build up pressure to then cause this explosion. If instead we fill up this little device with the same amount of black powder and then just screw it into here, the gas will release so much quicker and it'll generate enough force to actually crack the rocket open. I should also note that most motors have this black powder charge designed into the top of them that goes off after a certain delay. You don't necessarily need electronic deployment, but it is better because you get to precisely control when it's happening. So finally, that leaves us with the parachutes. Now, once the rocket breaks into two pieces, you want to have shock cord connected to 2 points, one there and one there so it can stay together. And then attached to this, you'll actually have your parachute. Now for rockets that go to a higher altitude, you typically want to deploy a drogue chute at apogee so it can slow down the rocket as it comes down, and then have a flight computer reading the air pressure to infer altitude, and then once it gets to a low enough point, then release the main to slow it down to a safe speed. If you don't do this, you're going to be walking 5Ks to get your rocket. As an experienced idiot, trust me, it's not fun doing that. And that's pretty much all there is to it. If you understand those principles, you can pretty much build a rocket. Like and subscribe to find out next time how to do all the maths we skipped out on today without having to do any of the maths. It's pretty grouse.